So thank you. So today I will talk mostly about object-oriented implementation written in 3 different languages, and this work was done mostly a year ago by Sylwester Rabas, myself, and Anna Jarecka from University of Warsaw, and also in collaboration with Maciej Fiałkowski from PyPy team. And I will talk at the end a bit about my current work that is done at National Center for Atmospheric Research in collaboration with software scientists, mostly Davide Del Vento. So, just few words about personal background. So I did my master in theoretical elementary particle physics. So basically, I didn't really have experience with computational physics. And I just jumped to computational, mostly 477 atmospheric physics. And that was a big change for me. It was kind of fun, but I also had some lessons that I had to learn. Basically, that the software design actually does matter. And it's not only performance is important. And it might be obvious for you, but at many different conferences, it's not. And the other things that I prefer actually Python and NumPy. So, so that was my personal feelings, but also as you can see, it's not unique actually. People write it about in Nature and PhD comics, so I believe it's not only my unique experience. So in my title is object-oriented programming. And so why did we try to use the object-oriented programming? Actually, it's like quoting the numerical recipes, and that actually it's it should be pretty basic approach for complex software. And actually, when I talk with people from outside science, it looks like it's pretty obvious for everyone. But actually, in scientific world, actually, I haven't had many experience with object-oriented programming. So we just try to explore this problem a bit more. So what was the most important things for us, using OOP programming style? So mostly we believe that with using object-oriented programming, it's easier to separate different program logic, so you can separate the real physics from the numerical problems, from the, for example, error handling. So this allows actually that you can have different people in your group working on something completely different parts of the code very easily. And the other thing is that we believe that it can help to shorten and simplify the source code by reproducing the mathematical notation, and I will talk later about this more, because it's actually it's one of the biggest issues that we try to keep in mind during writing the paper. And we believe that both these things contribute to maintainability, and what is actually pretty important if you want to reproduce a science. So this is the paper that was actually, I think the link started working a week ago from Scientific Programming. And so, as I said, we try to translate mathematical abstraction in our code written in C++ using Blitz++ for array, and Python with NumPy, and Model Fortran. And by Model Fortran, I mean the 2008 version where the object-oriented programming was possible. So the idea was to take pretty simple but pretty simple algorithm that is also used in really weather and climate models. Discuss all the code in paper and compare the language library pairs. So the code is on GitHub, and the earlier version of the paper you can find online. So now I will talk more about OOP implementation and advection scheme. So since it's not geoscientific group, I will just say a few words about numerical models. So basically in physical numerical models, we calculate in each grid box all equation for all variables of model. So of course the performance depends on how big is your domain and how many variables you have. And it's like the advection is actually like the very basic equation, that's very basic physical process that basically tells you that that the cloud is moving from one place to the other because with the flow. So this is like really, it looks like basic equation, and when you want to like translate it to like more numerical scheme, you usually just take the values of the scalar in the last time step and calculate the advection part. So mostly like it's quite common to use what is called Arakawa grid. So basically you calculate the scalar fields in one point and the velocity in between. And the simplest scheme is the Donner's cell scheme, that basically you just check what is on your left, what is on your right, and if it's moving in your direction or not. And this is the simplest scheme you can have. So, and it was in 1D. When you go to 2D, of course, it's like you have additional terms, and like writing like LaTeX or on a piece of paper, you actually use some mathematical abstraction just to not extend this equation for many different parts. So like here, it's like basically you have the same advection scheme in each direction. So you can add some sum, you can have some permutation operator just to change the indices, and it's pretty normal, like writing paper. And this is like, so that was the basic Donner cell formula. And we actually use the MP data scheme. This is more complex scheme. I don't want you to read this equation. I just wanted to say that like the few points are that actually, I'm still talking about this very simple equation that I started, an advection equation. But if you want to force your model to do it in a right way for many time steps, you actually end up like with quite a number of equations, and in each parallel model you have at least few different advection scheme with many different options. And if you don't really think about it, you end up with like big mess and in a code. And the other thing is that you use, like as I said, like using LaTeX, you use actually a lot of some very obvious for us mathematical abstraction just to also shorten this code, and it's it's clear to read. So we also wanted to repeat this mathematical abstraction in our implementation. So basically, what do we mean by this? It's mostly it's that we want to have our code to loop free, and it looks like more like LaTeX implementation. So for example, like with object-oriented, using object-oriented program, like libraries like NumPy, and using object-oriented approach, we're able, for example, to overload some operators just to make our implementation as close as LaTeX text as possible. And actually, when you go to 2D, you also see that using this approach, it's very easy to extend for a multiple dimension. You can also represent a permutation operator, and that permutes your indices, and it's very easy to represent the advection in many different directions without extra copy-paste code. So now I will compare this. I won't show the code for C++ and Fortran, but I will just compare performance and some trade-offs. So what we've done was simple experiments. So we had at the beginning we had Gaussian shape, and we did our experiments. We ran different simulations for different sizes of our domain. So starting from 64 to 64 to 2048. And the time of the simulation was actually kind of normalize that to have more or less the same time for all simulations. So, and as I said, we did it for like 3 different implementations that we really try to keep as similar as possible. So, and this is our result for the CPU time divided by time step, etc. So, so the red one is Fortran using. We only use the open source compiler. So this is like the G-Fortran, and the black lines are two C++ compilers, the GCC and the Clang, and the blue line is the CPython implementation. So it's obviously it's much slower, but what was actually surprised us a bit like that the C++ implementation was not so far from Fortran. And the other thing is that the memory usage. So it's also like the ratio of peak memory use divided by size of actually like our arrays that we really needed like for variables. So basically, if there is no temporalize, it should go to 1, yeah? It's not very important what is here, because at the beginning the sizes of the arrays are very small, and it's much more important what's the size of NumPy library, etc. So basically what is like, what surprised us here, that actually the C++ Blitz work better than the Fortran, OOP Fortran, of course. So, and we also asked us if it's a way to improve the Python performance, because obviously it doesn't look very good. But so we decided to try PyPy. And so what is PyPy? I mean, it was actually mentioned today during the keynote talk that it's actually, first it's alternative implementation of Python with the JIT. And it's developed. The goal is just to improve the performance, but also they really take care that just to keep the compatibility with CPython. So why do you use this with PyPy in this context? Mostly because in version 1.9, it had like the JIT power lazy evaluation mechanism that can avoid having like many temporalities in NumPy. And the other also very important things, because you can also think about Cyton NumPy and NumX, that was the only solution that really allows you to speed up your code without almost any changes in your code. So, so that's how it looks with PyPy. So this is PyPy, this is CPython. So as you see, the performance is actually like, it improved a lot. And it was more or less twice faster as the CPython. And also what is very, very important that you really can see that that the lazy evaluation work, because the temporalize, there is not so many temporalize as in CPython, yeah? Because it goes more or less to the same value as C++ with Blitz. So PyPy performance, I think, is very promising. However, it's still like the NumPy PyPy, the package that they have to rewrite to in PyPy, is still under development. So it's not everything that was in like 1.9 version. It is in the current version, for example. They're still working on many different issues. So, but it's still promising. So that was like the comparison of performance, and there are other important issues that we also compare in our paper. So basically, if you want to compare the Blackboard abstraction, you can represent actually in each of this language. However, I mean, I won't talk about details, but in Fortran it definitely is the hardest, yeah? And if you compare the ease of use, that is also, I believe, it's very important when you talk about science and how not only performance of computer is important, but also performance like in your work. That Python is definitely the easiest way, the easiest code to learn, teach, and to debug. And what is very good, actually, I mean, I didn't think about it before, that what is really good in Python community, that NumPy is actually adopted library for any other scientific libraries. And it's not true, for example, in C++. C++ world, that, for example, Blitz++ works pretty well, but the problem is that it's only one of many libraries with the same application. Another issue that we compare is like what is good in Python and C++ comparing to Fortran, that is actually general purpose language, and this affects the people that you can find for working with you. And now I will just talk a few words about like our current projects. That is kind of, you can think about some kind of extension of the work that we've done. That what we learn during this project, I mean, that Python is great, but everyone probably knows this. But also, like, in some cases, C++ can also offer you something more. And what, for example, we use in our project, that actually C++ offer for three-dimensional analysis using bus units. And we actually didn't find anything in Python, maybe it exists, maybe you know, that's something that can change that physical units without any computational cost. What is also important that it looks like still there are some issues with Python and the HPC and GPU calculation. I mean, I believe that it's getting better, but still it's kind of like, I think, like the Trust library for C++, it's quite good comparing what we have. And what was also good that actually like Blitz has assured that you have high performance error manipulation without temporalize, without anything to do, yeah? So that was the difference. And so what we're doing now actually, like, so my colleagues from Warsaw were actually developing like C++ library. And one is the parallel solver for a system of transport equations, so basically a vector equation with many different options. And the other is for standing arousal on cloud microphysical algorithm. And we decided that actually the libraries are written in C++, but let's try to use it from the Python. And that's why we decided to use BoostPython, and my colleague wrote some code using BoostPython. That it's basically, we had like nice tutorials, but for people that don't know what's that, it's like, it allows basically for communication between Python and C++. It allows calling C++ library from Python, but also it allows to code some hard part in Python and send to C++. And why do we use Python in this context? I mean, basically, for our approach, for our case, the most important thing is that it can speed up the Python code, just calling some expensive, computationally expensive parts from C++. And what is other thing is for C++ library, actually it offers like very nice tools from Python side, for example, for testing. And that's basically what we're doing now. It's like, I just started this work, but actually we just decided to use so the first part of the work is just that I took this C++ library and just trying to test it, just to check if they are doing what they should do. And actually I used like PyTest. It's like, I don't have a lot of time to talk about it, but it's like, it looks like pretty nice library that offers like this PyTest mark parameters that you can, compare. Oh, sorry, this is actually for the, I'm testing if the C++ library actually calls rise exception. And it works, I mean, BoostPython definitely could send some exception. It's like all exceptions always are almost runtime exception, but you can still check it if, for example, a library has exception if your water is negative or such a things. Or, for example, comparing with analytical solution and for many different parameters using like PyTest mark parameter size, and it's pretty automatic and it's nice. And the other thing, what is you see here, actually I'm calling lib name. So basically, the idea is just to use the same exactly testing framework, just to test the C++ library, but also just to test with some other well-established models, other well-established microphysical scheme. And for example, from like for example, for the work scheme, yeah, it's very easy to convince someone that your new microphysical scheme works if you compare, for example, from the work scheme. And that's actually also Python is very good in it, because it's like Python actually allows you like using meta function and fixture names. Actually, I was able just to like use the same testing framework for like C++ library and Fortran library. And like just like last words that Python definitely offers not only bilingual C++, but it's also Fortran. I mean, I know there are many different libraries. I use CPython library, that is like C foreign function interface for Python, and it was like I spent some time, but it definitely works. Yeah, so that's just the take-home message is that basically that the PyPy is it's promising, and its Python is really allows to very nice binding and testing with other libraries, and it also might be worth of using. And thank you.